Hi, I'm Howard Wetsman, Chief Medical Officer of Townsend. I want to introduce you to the idea and word pharmacogenomics. Pharmacogenomics is using genetic information to make decisions about medication. It's why your doctor cares about your genes. Genetics are important because that's how we're born. We're born with our genetics. We are the sum of the genetics we're born with and the environment and experience we live through. Our genetics are encoded in DNA, a long, stringy molecule made up of building blocks called nucleotides. When we refer to our genetics in its entirety, we call it our genome. Our genome, made up of these 3 billion nucleotides, are split into 23 different chromosomes. Everyone has 2 copies of each chromosome, except for the sex chromosomes, X and Y. So you can see in this picture that there are 2 copies of chromosome 1, 2 copies of chromosome 2, and so forth. Notice at the bottom right that females have 2 X's and males have an X and a Y. So these 2 copies come from our parents. We get 1 copy from our mother and 1 copy from our father. Now, because men have an X and a Y, we can only get the Y from our father. If we get a Y from our father, we're male. If we get an X from our father, we will also get another X from our mother. We'll have 2 X's and we'll be female. That's how it works. Let's just focus on 1 chromosome for now. So at one point in the production of eggs and sperm, the copies get separated so that one or the other is passed on. Here are the copies blown up and separated. Let's look at just 1 copy and blow it up even more and see that it's actually made up of 2 strands of DNA. Now let's look even closer by blowing this up so that we can see the different nucleotides that make up the different strands. Now let's move this up and get a better look. Remember, it was a double strand of DNA. We'll bring back the other strand to see how they fit. So now we have a close look at a bit of 1 copy of a chromosome. We have here 4 letters that represent the nucleotides that make up our DNA: A, T, C, and G. Notice that A is always paired with T and C is always paired with G. That's just how they fit chemically. So if we were to read from left to right A, C, A, T, G, G on the blue, or T, G, T, A, C, C on the red, we're really reading the same thing, even though it sounds different to us. So this is a close look at 1 copy of a bit of chromosome. But remember, we have 2 copies of most. So let's bring back that other copy. And let's say we got the top one from mom and the bottom one from dad. Humans are an exact match with each other in almost all their DNA. Only in a few spots are we different. That's why we all look human. In fact, chimpanzee DNA matches about 98% of human DNA. It's the other 2% that makes us human. And humans are a lot closer to each other than chimpanzees are to us. There's really less than 1% difference between any 2 humans. So even though mom and dad don't look alike, except for their X and Y, their DNA will be boringly alike. If we look at the sample below, we see only 1 difference. Reading blue from the left, from mom we got A, C, A, T, G, G, A, A. And from dad we got A, C, A, T, A, G, A, A. So at just that 1 spot, we could say we have GA. We can't tell what mom and dad had, just that we got 1 from each. Since we got G from mom, she could have had AG or GG, but not AA. She had to have at least 1 G to give it to us. Since we got A from dad, he could have had AG or AA, but not GG. He had to have at least 1 A to give us. This kind of difference is called a SNP, abbreviated SNP. SNP stands for single nucleotide polymorphism. Only 1 nucleotide is changed, so that's single, and polymorphism just means more than 1 form. Not everyone is G, so there's more than 1 form. We all have hundreds of SNPs. That's what makes us individuals. It's not good or bad, it's just what is. So we have this SNP. That means at this spot, we have a nucleotide that most people don't have. In this case, let's say 60% of the people are GG, 30% are AG, and only 10% are AA. Well, so what? Well, maybe nothing. It only matters if this polymorphism produces a change in the function of the gene or the function of the protein made from that gene. It could change that function for better or worse. Not every SNP causes a decrease in function. Some cause an increase in function. In this case, let's say that this is the gene for the opioid receptor in the brain. And let's assume that when G is there, everything works fine. But when we have an A, the receptor is a different shape, and it doesn't see the brain's opioid as well. So in this made-up example, someone who has AG has half of their receptors working well and half not so well. In total, their opioid receptor function would be lower than normal, and so the function of their brain's own opioid system would be low. Such a person would not release as much dopamine into the midbrain reward center and would not experience normal reward from normally rewarding experiences. Such a person would tend to like opioid medication that stimulated the opioid receptor up to normal levels. So such a person might be at higher risk for addiction and for using opioids in the illness if they have it. Now, what I just gave you is an example where a SNP would directly change the function of protein by changing its shape. There are many other ways SNPs can affect health. Most of the genome is not made up of genes that code for proteins. Much of it has to do with how much the genes are turned on or when they're turned on. Some parts of the DNA act as promoters. Promoters help to determine how much is made from the gene that they're next to. So let's say this part isn't for the opioid receptor, but for the promoter of the opioid receptor. In that case, the receptors that are made may be normal, but you just may not make enough of them. There are other regulatory areas as well that don't determine the shape of a protein, but how it's made. A SNP could be something that makes a difference, or it could be something that makes no difference at all. In that case, we would say it's silent. So if we start with the 3 billion nucleotides in our genome, and less than 1% are what makes us human, that's still 30 million nucleotides. Most of that is going to be the same in all of us and not get mutated, because for a SNP to be in the population, it has to be survivable. So let's say as much as 10% of that is so unimportant that it could be mutated and we'd survive. It's probably much less than that, but that's still 3 million nucleotides. Most of those will be silent, but still be a lot, over 1 million, that can affect the function or the amount of the proteins we produce. Some will change the proteins, but in ways that don't matter, giving us different skin color or hair. There's a lot that doesn't matter. Kind of earwax, whether we like blue or red, or if we have long or short earlobes. There's a lot that's genetically determined that has nothing to do with health in the modern world. But out of that 1 million, there could be tens of thousands that affect our health. And of those that affect our health, some will affect addiction.